So welcome everyone. I will continue with so-called transformers, and the idea that goes behind transformer is some of the ideas that's also taken from sequence to sequence model, attention based ideas, and then also masking, let's say, uh, and also ideas such as query keys and values that's taken from information retrieval. So if we look into the problem of let us say information retrieval, then let us say we have a dictionary with these values, and let us say green with this value 0 to 550. Then we have blue 0 0 to 55, then yellow, and then we have 255 2550, and then we have, let us say, purple, which is 255 255, and then so let us say this is the dictionary we have, and let's say this is a Python dictionary, and let us say we want to query for query for D, let us say is blue. Then this is our query, and in the query we look up in the dictionary, and in the dictionary then we look up, then the value that it will return is 0 0 255. Okay, so the sequence to sequence model that we have seen before, I can quickly draw this, and we have h1 h2 h3 h4. So let us say we use a two layer of the h. Okay, then we have the input is dead and so on. Okay, so in this we recall that we computed this f vector. Okay, so there were only let us say 4 inputs in this case. Okay, so you recall that we calculated these f values, okay, and which was later used as in the softmax to calculate the attention weights, which were alpha 1, alpha 1 1, so alpha 1 2, alpha 1 3, alpha 1 4, and later from here we use this to create a context vector alpha ij hi. Okay, so this is what we recall, and then this context vector is used, let us say, in the decoder phase of S0, and then combined with this we concatenate this with the input, and this S0 is used when computing these f, which depends on hi and S0. So we have done this previously, and based on this this is calculated. So we can have a view of these query key value view of this as well. So for instance, here we can think of this as a query that we have for the output of this here, and then we query this with these outputs here. So this in some sense acts like a dictionary for us, and then we look for what is the best context of the output that is going to be produced, and which is the word that has the most influence. So this is already created by this context vector Cj that indeed gives you. So this context vector, unlike the dictionary, what happens is that in a dictionary you explicitly go and pick which was the blue, and then you produce that. So here it's not necessarily like that. Here we go and look for these attention weights, and then these attention weights are calculated like this, and rather than giving one of these inputs as the data that I want to retrieve, it gives me a combination here. But obviously the one that has higher weight will have more influence here when I retrieve that. Okay, so so it's a further remark on this. So encoder hidden states can be thought as an information store at each time step. Decoder can be seen as querying this information store. And current decoder state, let us say, so initially we have S0 and then we have S1. So let us say the current one is S0, okay, so or S1, let us say the current decoder state S1 serves as a query, okay. So we try to model this as a information retrieval problem where this is our query. Initially it should be S0 and then it's looked at S1, and this query is matched with this information store. It's not exactly like a dictionary, but then from there what we retrieve as a as an output is this context vector C, okay. So this idea of key query value is used in modern day architectures like transformer that we will study today. So this is the idea. So intuition could be, we can get a bit of intuition from here when we go and develop a transformer architecture, but there are a few more ingredients. So as I said, rather than picking one match from the dictionary, it's not necessarily the case. So here we, the query, the value that we get will be in the form of a context, which is the CJ vector in this case, which itself is a linear combination with attention weights and HI vectors. Okay, so so this is the motivation or the way we are going forward with this. We will extend these ideas further, and now we will study transformers. So if we look into transformers, so transformers were proposed in the paper Attention is All You Need by Assis Vaswani, and the year, I'm not very sure, I believe the year was 2016 or 14 somewhere, okay. And so this is again a form of, so basically there are two primary blocks, so encoder and decoder. So just in sequence to sequence model, which are also encoder decoder model. So we will focus on encoder first, and even before that we will recall tokenization. So the kind of tokenization used in these transformer architectures, so it's a little bit different from the traditional one. So I will quickly go through that. So if you recall tokenizations, then given, let us say, a text where can I find pizzeria. So let us say this is the text we have. Then we have the tokenization problem means how am I going to represent this as a vector, okay, so that each have their unique representations. So everything has to be translated into vectors and so on. So here if we see I can do it word by word, so each word have a unique vector representations, or I can do it character by character. So W is a character, it has one representation, H has one representation, space has one representation, and so on. Okay, so traditionally we can think of two types, word level and character level tokenization. So we can see it here. So word level tokenization, and we can look at character level. So we can kind of look into these two, and then we will define something called subword. So let us say if we do a word level tokenization of this sentence, where can I find pizzeria, then I can write this as where can I find a pizzeria, right? So this is the tokenization. If I look at the character wise, then I will, so what are all the words, I mean the characters that you have here? So I can find A, I can find C, I don't find B, right? So I have A, C, D, E, F, H I N P R W Z. So this is this is the tokenization I can use for this sentence. So I don't have a B, so I didn't put B there. Similarly, I had many other characters which were not there, so I didn't need those. So we have some positive and negative. So in this case, word level is more intuitive, because usually we usually understand words, okay, and because they have meanings as well. And the negative of this is that it does not handle out of vocab words, including slangs or let us say play on words or misspellings. Okay, so if we do it indeed word level, then if there are out of vocabulary words which is encountered, then there is no way that it can represent that. And if our corpus, meaning all the text that we were going to study, let us say that's our corpus, then if in our corpus there are many words, then our representations for these will grow, because there will be many words. Okay, so here we have use vocab for large corpus. So it will be a big list. Okay, and also in a word level, handling punctuations is challenge. Okay, so punctuations is challenge. Okay, so for example, things like don't. Okay, so should we take it as do not, or should we take it as one whole word? Okay, and also abbreviations, let us say NYC, N.Y.C. So should we take this as a whole word? Okay, so these are the things one have, positive and negative word versus all. But then we can also look into let us say character by character. So this has small memory footprint. So that's evident, because the total number of characters, if you think of 26 English alphabets, okay, and you may also take into account, let us say, capital letters, and then some special characters also going into some number, let us say 40, 50, whatever is relevant, but still it will be around 100 or something like that. But number of distinct words can be many, as you know. Okay, if you see dictionary, then so here in character you may have very small memory footprint, and of course if the corpus has very limited number of words, then this may be a good idea, but then for very large one it may not scale that way. So and then it also handles out of vocab words. Okay, so if there is a word that was not seen in the dictionary, there is a slang, but even those slangs will be created from these alphabets only, so they can still be represented. Okay, so out of vocab words can be represented. In other words, this can give you more generality. So the negative of this is that it needs to go over all the characters. So needs to go over all characters and learn a particular sequence for a given word, and there is sometimes like loss of performance, because in this case what happens is that if you do character by character, then you're not giving the whole word context to the model. Okay, it has to figure out the words from characters first also. Okay, so it although it's more general, but then it has its own problem. So these are the tokenizations. So what modern day language models use is something called subwords. So that's also used by the paper that introduced transformers. So there are more authors, by the way, here. Okay, and there are, I believe, 5 or 6 more authors. I have not listed them all. So we look into, for transformers. So transformers take a middle ground for tokenization. So this way of taking text and then representing them in some vectors, this process is called tokenization. Okay, so transformer tries to take a middle ground in the sense that it keep frequent word as is, okay, keep it as it is, and break the rare word as commonly occurring subwords. Okay, so there is this concept of subword. So let us see this with an example. So let us see subword tokenization. Subword. So if you look at subword tokenization, so let us say, where can I find a pizzeria? Okay, so let us say this is the sentence that we anyway started with. So we may use a subword tokenization. So the commonly occurring words are here in this case are where can I find a, but pizzeria may not be common, so we break this into subwords. So in this case it will be, let us say, pi ZZ ERIA. The subwords may not make sense by themselves, but it may be that those subwords are common. That's the point. So here ZZ may not make sense. Area also may not be a valid word, but or these subwords by themselves may not be very common, but still we break them because these subwords may not be common as a meaningful word, but they may be common in many words as a small part of that word. So that's the point. So in this case we do that, and let us say we encountered a word, let us say listeria. Then listeria is also a rare word, so this could be broken down into let us say list, and then also let us say area, ERIA. So if we have included this subword ERIA, then we found that subword ERIA is also in this rare word listeria. So we can have a subword decomposition of these words like that. So this is called subword tokenization. So this is some way it's a middle ground of not going very character to character level, remaining at word to word level, but then not trying to represent all unique words, but rather breaking them in a way that those small portions, although they may not be meaningful word, but they are quite common. Okay, so one of the other examples could be, so for instance we can also look at the words for instance disown or disengage or disconnect, disarm. In all this subword dis by themselves may not be meaningful or very as a standalone may not be used, but this is a good subword to have because this is used in many places. Okay, so we can also look so while doing this, maybe I can also introduce one of the work that we did is hybrid tokenization and data set for solving math and science problems using transformers. So this was done with my students Pratik, Snehit, Neeraj, and myself. So in this, what we propose is a way of tokenization for the transformer itself. So here we were solving maths and science problems. So basically maths have also very special characters like integral and then let us say parentheses, various types of parentheses, and many characters that we encountered while writing maths. So we proposed a hybrid tokenization where we had the words, and then for those characters we had and these hybrid tokenization schemes. So for more, obviously you can go and look into these papers. So the way we tokenize also plays a role in the accuracy or the way transformer learns. Okay, so this is the first thing basically the transformer sees, right? What goes as an input. Okay, so coming back, so for instance we can also look into tokenizations like let us say something called byte pair encoding. So this is another way so it's essentially a data compression algorithm. So Let us see another example. C cells, let us say cells, 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 C cells by the C. So if there is a text like this for an example, then we can look into, so if we look into the vocab of this, the vocab list of this, then we have space character, and then we have A, B, E, H, L, O, R, S, T, Y. So this is the list of characters we have, and in this list of character we may want to add some frequently occurring subword. So in this case, by subword I would mean, let us say SH. SH appears here, SH appears here, and I guess by the seesaw. Okay, so the seesaw, SHORE. So there is one SH appearing here. So this suggests that, okay, you maybe you go by the character only, but then you add these subwords like SH. And similarly, I can look for other ones, like let us say HE. So if I look at HE, then this is HE, HE, and I believe HE is also here. So it is worth putting maybe HE also inside the encoding. Okay, so this is another way to. So basically, you look for the subwords which occur very frequently in your corpus. So in this case, SH appeared 3 times, so I added that. The next HE also appeared 3 times, so I added that. So this way also you can build a tokenization. Okay, so so basically, if we look into the transformer architecture, then we have on the coarse scale, we have input sequence, or we can say tokeners, where we have these subwords can, I, and then find, pi, z, and then area, which we discussed before. So this is, let us say, subword tokenization that we discussed just now. And then once you have that, then after these tokenizations, that they become a vector of some form, let us say x1, x2, x3, x10 or something like that, and then it goes into, so this is our embedding that happens, and then it goes into the encoder block that we will describe now. Okay, and similarly then there is also a decoder block in the transformer. So basically, yeah, so from the encoder block, and then there is a role for this decoder block. More specifically, we will discuss this. So this is for the moment the role of the subword tokenizer. It gives you a representation for the sequence that you are going to input, and then this goes into so-called decoder block. Okay, so now why are we interested in transformer architecture? So to motivate that, we can kind of look into RNN very quickly. So shortcomings of recurrent based attention. So if you recall, the attention based, the sequence to sequence, or even RNN that we have been discussing are like this. Okay, so in this case it will be where can I find a pi, and then ZZ, and then ERIA. Okay, and then from here we have these outputs or the hidden representations that we have. So what might happen is that, for instance, let us say we have H4 here, then computing this, computing H4 requires all previous time steps to be computed first. Okay, so computing H4 requires all previous time steps to be computed. In this case, I will need H3, H2, H1. Okay, so this is the and what is the problem then, right? So if I use H4, if I have to compute H4 and it indeed needs previous time steps, then what is the problem? The problem is exactly this. It has this sequential nature, okay, which essentially means that that the computations can't be parallelized. Okay, and there is a bottleneck on training with this approach. So this is a bottleneck for training large data sets. Okay, so this is the bottleneck. These are the problems that transformer tries to resolve, that is essentially sequentials to go one after the other, and there is a bottleneck, and this is exactly a bottleneck because I cannot parallelize, and modern day computing machines are multi-GPU, multi-CPU systems, and their having parallel approach helps a lot in training it faster. Okay, so and the third issue is, so the third point is that final hidden state has to capture a lot of long distance relationship. Okay, that we saw, like even when we started with RNN, this was indeed an issue, long-term relationship, and so on. And so for short sentences, this is not a problem. The final hidden state will more or less represent all the previous ones, but for the long sentences, this could be an issue. So attention is exactly the reason why attention was introduced, to look into the previous ones. But again, it still does not solve the problem when we go to the decoder step. Okay, and this is something we will see now with the transformer. So hence we now do a transition to the transformer, and the key idea. So the key idea behind transformer is, we first describe it very broadly, and then we go into detail. And then we have some form of something called let us say, alternate mechanism that we will describe. And then with this mechanism, what is happening is that the first output that I have, the output corresponding to the first encoder, will be based on all inputs. So basically looks up into all of the inputs. Okay, so the output corresponding to first encoder will be based on all inputs. Okay, so that's one thing, and it's not just about the first one. If I'm going to produce the second output, then let us say the fifth output somewhere here, then this also looks up into all of these. Okay, and this mechanism is the main idea behind, one of the key ideas behind transformer. So the idea then we can write is that throw away the recurrence, and base each encoder output to all encoder input. Okay, to all encoder input. So base each encoder output to all encoder input. Okay, so this is the key idea behind transformer. Okay, and this idea gets repeated multiple times to create something called attention head, multiple attention head, and then you get encoder block, and then there will be multiple of these encoder block. In the original paper there will be 6 of those. So that's basically one of the key idea, and another key idea will be to see this as an information retrieval. So we will see that. So we will separate key, queries, and values. So we will have a view like that, and that leads to something called attention mechanism. Okay, so what transformer does is that this alternate mechanism is something called self attention. It is self attention because it is looking up on its own inputs basically. So the output that I'm going to get here is not looking elsewhere, it's just looking here, and the inputs themselves. We are not talking about any feed forward or neural network that have processed this, not we don't do that. So we just look into this and how it is associated with this. Similarly, this guy, how it is associated with this, and itself. and this guy how it's associated with. So this initial step is called self-attention. Okay, so then we can kind of make it more precise. So let us do it here. So let us first develop a simple variant of self-attention. So here we will not bring in the concepts of key, query, or value as such, but we will first just see a very basic variant of what self-attention could do. Okay, so simple variant. So let us say we have two inputs. Let us say we have three inputs basically, x1, x2, x3, and then by self-attention we would mean that we take dot product of x1 with itself, then we take dot product of, so basically, so let me draw this a little bit far apart. We do this for the first output itself, so I need some space for the second, then I need some space for the third. Okay, so these are the three inputs we have, and by self-attention, what we do is okay, so this is x1 with x1, x1 with x2, so that x2, and x1 with x3. Okay, so that can give me a score. So this is dot product, so this gives me, let us say, s11, s12, and s13. Okay, so this x1 dotted with x1 gives me s11, x1 dotted with x2 gives me s12 score, and x1 dotted with x3 gives me s13 score. And then I apply softmax. So as you know, softmax takes a vector, in this case length 3, and will give you kind of a probability or the attention weights in our case. So this is A11, A12, A13. Okay, so that's what we get. And then obviously, like let us say some context could be generated based on this. So Aij or alpha ij and taken with xj, okay, and j is, let us say, 1, 2, 3. Okay, so yeah, so this is alpha 1 and j is running from 1 to 3. Okay, so some kind of context could be created, and we have also seen this in the encoder decoder model and so on, but we are moving towards transformer basically. So this is the self-attention. So basically the output that I'm creating is looking is from the dot product taken from itself, and then dot product taken with the second one and third one. Okay, and that is used to produce this. Now similarly I can do this for the same guy, but then here it will be x2 that will be taking dot product with all others. So x2 with x1, x2 with x2 itself, and x2 with x3. So this x2 with x1, x2 with x2, and x2 with x3. Okay, and same way I can proceed, and in this case I have s21, s22, and s23, and then this gives me attention a21, a22, and a23, and from there I can again compute some x hat 2, which is a2j xj j equal 1 to 3. Okay, so this is a very basic idea of how we can create a simple version of self-attention. Now we will try to kind of extend this idea further. Okay, so what we observe in this process is that every output is based on all inputs. Okay, there is also no need of sequential processing. There is no need of sequential processing. Okay, because all three computations, as you can see, could be done in parallel. Okay, this x1 axis you have, x2 you have, x3 you have, they have nothing to do with each other. This, and this third one could be computed simultaneously. That's parallelism you have. So computing self-attention could be very fast. So the next step is that although we know that okay, everything can be, it is indeed parallel, but when we can stack these into matrices and then do this in one shot. So basically if you see here, I am multiplying x1 with x1, x2, x3. So basically what I see here is that x1 let us say I denote this by one vector row, and it's multiplying x1, x2, x3. And then in the next step, I see x2, and this is being multiplied with x1, x2, x3. And then I have x3, then multiplying x1, x2, x3. This is x1, x2, x3. So what we see here is that all this operation could be made into a vector. So basically the x1 applies with x1, x2, x3. Here x2 multiplies with x1, x2, x3, and x3 multiplies with x1, x2, x3. So if I collect this x1, x2, x3, then and row by row, if I do that, then indeed I can vectorize this. So if I use this, so I could have stacked x1, x2, and x3, and then I have x1, x2, x3. So this is indeed a transpose of this. Okay, so this if I collect all the x1, x2, x3, then this could be seen as x transpose x. Okay, so this is our x, and we can see this as or the way it is written in my notes is that I treat this as x and this as the transpose, because I have the x, let us say, stacked like that, let us say. So this is basically the operations that we do is this operation that we do is basically x transpose, and then the first row that I get from here, x1 transpose x, so what I collect in the first row is exactly the values s11, s12, s13. And similarly x2 with x1, x2 with x2, x2 with x3, this gives me s21, s22, s23. Similarly s31, s32, s33. So I got these s values here, and then previously I wrote some s values here, and then the third one I wrote this. Now I got all this in as a row. And similarly I can apply softmax on each of these row by row. Softmax applies on this. Okay, so basically I apply softmax s11, s12, s13, and similarly I apply softmax for the second case that I have just rubbed, and so softmax will apply on second row and then third row to give me the attention weights a11, a12, a13. So if we apply softmax, then we can use this board. So if we apply softmax on this, then we will get a11, a12, a13, and a21, a22, a23, a31, a32, a33. So these attention weights that I was looking for, and from there the context vector and everything can be calculated. So this whole operations can be stacked as a matrix, and matrix operations, as you know, are pretty much parallelizable, matrix multiplications in this case, and then parallel applications of softmax. So all this goes well in this modern day multi-GPU, multi-core machines. Okay, so hence it helps training these networks. So the next step that came in the transformer is that the first step is obviously this self-attention, but this self-attention is also not applied in exactly this form, and there will be a slight change here. So this is something I am going to discuss next. So what we are going to discuss now is this scaled dot product attention. And as I said, the way the self-attention that we did was a kind of a template, but then the way it will be applied is in terms of query key values. So this is another concept that we would like to learn. So the way it will be done as follows. So we have a vector x1, and it has a vector representation, let us say 4 components, and then what we can do is we can, so I would prefer to do it from bottom maybe. So let us say from here. Okay, so this is our x1, and then from here we will create 3 vectors of query key values. Okay, so this is one of the key ideas also of this paper. Attention is all you need. So W for key, the weights, and weights for the query, so that if we multiply, then we get a query vector. Okay, so the dimensions are such that I still get 4 output with 4 components. And so let me draw this a little bit. So let us say we have WK, so the weights for this, and then this gives me a key vector, and then we have WV, the value, okay, and then this gives me value vector, and then this gives me a query vector. Okay, so from x1 I multiply a matrix wq, and then this gives me a query vector of length 4. And then I multiply a vector matrix of for the key, and then it gives me 4 length query vector, a key vector, and then similarly we get a value vector. Okay, so and then now we apply something like self-attention. After we have done this query key value separation of the input from the input vector itself, now we kind of develop something what we done before, which is a query key, I mean self-attention basically, between query and key value. So the way it goes then as the next step is that we have q and k. So this is q1 k1, and then we have q1 k2 and q1 k3. Okay, so q1 k2. Okay, 1 2 3 4 1 2 3 4 2 3 4 1 2 3 4. Okay, so this is what we have now, where we are. So but this key k is obviously it's using k from here, but it's also now looking at k from the second input, which we have not drawn yet, but we can draw it now. So what we can do is take the second one, x2, and then it has its own weight here, and then wk, and then we have wq, and then okay, so this produces its own query key and value vector. Okay, so query key and value vector. So 1 2 3 4 2 3 4 1 2 3 4. Okay, so we can call this q1. Okay, this is let us say k1, and this is v1. Okay, so here you can clearly see k2 is now looking into this k. Okay, so v2 q1, and similarly in our example we also have x3. Okay, okay, so these are going a bit higher. So this is our k3, v3, and q3. Okay, and this is our q2, sorry. Okay, so as you can see, first we have divided this by multiplying with weight matrices. We have extracted query key values, and then when we are computing these values, is k1 for the first keys from here, k2 from the second, and k3 from the third is being used here to create these attention weights as a next step. So the next step is calculate attention weights, and from there obviously you can produce some output, which is alpha 1j vj. Okay, j equal 1 2 3 in this case. Okay, so and what in the transform network, what they say is that while you are computing these, let us say these are called scores, right? So this is S11, S12, S13. So let us say these are scores which are produced as S11, S12, S13, and these scores can be, because they are dot products, and if these are very big length, in this case it's only 4 length, but let us say if these are big length, then dot products could be very high value. So it suggests scaling this, dividing this by dk. So that's why we call it scale. Okay, and then so this process is what we are trying to elaborate here, and from there as usual we have softmax, and then from there we calculate the attention weights A11, A12, and A13. Okay, so this is the whole process that gives you these values, and the same thing is done for the other cases. In the second step again we will do the same steps, but so for the second step, just for iterations, what I will do is that again I will compute self attention now for the second step. So this will be q2, so q2, and then multiplied with k2. Okay, so So Q2 multiplied with K1 first. Okay, it has to look also previous one. So Q2 multiplied with K2, and then similarly Q2 multiplies with K3. Okay, this K3 is indeed obviously coming from here, and this K2 is coming from the self, and this K1 is obviously coming from here. Okay, so this way it produces its own S21, S22, S23 values, okay, from each of these, and then it goes through softmax again, and then from there you get this values alpha 21, alpha 22, alpha 23, and this is used to compute x hat 2, which is a linear combination of alpha 2j and vj. The value vectors are used here, j equals 1, 2, 3. These value vectors are in linear combination. So here in the v1 will be from here, v2 will be from here, and v3 will be from there. Similarly, this guy also values will be taken from all three. So this is the idea behind self dot product. Self dot product attention, and then again, like in the previous case, we can kind of make this into a matrix operations, because as you can see, just like in self attention, we could stack the x1, x2, x3. We can do similar stacking here. So basically we can stack x1, x2, x3, and this w, all the query weights we can multiply on each of these x1, x2, x3, and then we can kind of produce these individual k1, k2, k3, but now it will be produced as a matrix k, and then there will be a matrix q, and then there will be a matrix v. Okay, so it's possible that we kind of stack that, so that we can explain it here. So to make a space, maybe, okay, let's see if I can use it. So if I kind of try to write this as a matrix vector form, okay, so this I have combined this. So there are like 4 components in X, and then for each time I have stacked one on top of the other. So this means that the first row is X1, second row is X2, third row is X3, and then I multiply with the weight matrix WQ, which is of the form d by d, and then I multiply with the matrix WK, which is of the form d by d, and then I multiply. Okay, so maybe later on I will see what could be done with this value, but let us proceed with this. So if we multiply with the weight matrix Q on each of these sequence, then we will, what we get is, if I multiply with the query matrix, so this query matrix multiplied on x1, this query matrix multiplied on x2, this query matrix multiplied on x3. So this is what is happening: query matrix multiplied on x1, query multiplied on x2, multiplied on x3. So this will give me a stacking of query 1, query 2, query 3. So that will be our matrix. In this case will be q t by d. So there will be 3 query matrices. So t in our case is 3. So there will be 3 by 4 matrix. That will be the output. And then if we do the same thing for the key matrix, then we will get similarly a k matrix, let us say, and that, so we can kind of, if you want to visualize, then it will be like this: 1, 2, 3, 4, and then 1, 2, 3, 4, then 1, 2, 3, 4. So this is our q, which is t by d. And then similarly here we will have 1, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4, and this is again our matrix k, which is t by d. Okay, so these are the operations we did. We combine these operations as a matrix, and then what we do as a next step is that we are taking self attentions, right? So we're applying q1 with k1, q1 with k2, q1 with k3. So just like the idea we had before, q1 multiplied with k1, k2, k3, and then similarly q2 multiplied with k1, k2, k3, and then q1 multiplied with q1, k1, k2, k3. Similarly q2 multiplies with k1, k2, k3, and similarly q3, which is this, multiplies with k1, k2, k3. So just like before, we can stack this q1, q2, q3 as a matrix, and then multiply with k matrix, which is k1, k2, k3. Okay, so but this q1, if we stack it like q1, q2, q3, then it could be seen as a transpose. Okay, so basically, yeah, the key, we see rows as the key key value. So then in fact the transpose will be for the k, okay, just like we did before. So then this will be after multiplying, so we multiply this guy with this, so multiply, so what we get is 1 2 3 4 2 3 4 1 2 3 4, okay. So we multiply q with basically k transpose, okay. So actually this is k transpose, and then the multiplication happens of k transpose with q, and this gives me the attention scores. So this gives me attention score. So basically if I calculate attention score, then it will be t by because k transpose will be d by t, so this is d by t. So if I multiply d by t with t by d, then it will be t by t matrix, okay. And as before, we attention matrix or score matrix, whatever we have, we do prefer to do a scaling when as we said before, the dot products can be very high, so we may normalize this scale down by dividing by square root of dk, okay. And then we take a softmax over this, so and then from there we get the so this is the S matrix and then softmax, and then we get the attention weights basically. So from here we get attention weights, so this is all t by t, and then these attention weights, if you can recall, then these attention weights are kind of multiplied and then with the v, so this is our v, which is t by d, okay. And this is where also we have operated the w matrix on v, okay. So w v has been multiplied on these input x, so that led to this, okay. So this x was also multiplied with this value matrix, and then eventually this value matrix we get these value vectors, and then these attention weights do a linear combination with this vj. So this linear combination is now denoted as multiplication of the attention weights t by t multiplied with the value v by d. So you can check for yourself that if I multiply that attention weights t by t with t by d, it will indeed produce these linear combinations, okay. So this was the scaled dot product, and these operations that we have denoted, we can just write it in a very compact form. So let us say we do it here. So so what we have written there, we can also write this in a compact form in terms of matrix operations. So this is the stacking we have. So these are the matrices we have. So we have produced this matrix Q, which is T by D, and then we have the matrix K, which is T by D, and we have the matrix V, which is T by D. Okay, so all this is then we can compactly write whatever we have done as something called attention function that takes Q, K, V, and the operations that it does is essentially softmax of Q, K transpose. You can see there, that's what we did. This is the Q, K transpose that happened, and then we scaled it to get the scores, and then the scores are scaled by dk, and then we multiplied it as the last step with the V matrix. Okay, so V matrix already had this WV have been multiplied with this X. So this WV has been multiplied with X, and this is why we got this V matrix here. Okay, so this whole operation is called attention head, and this is single attention head. Okay, so as you can guess, there is a concept of multi-head attention. So that's the next step. So if we look into the multi-head attention step, then we can basically it's the same idea, but multiple of these heads will be combined. Okay, so let us see how that works. So let us in a multi-head attention we put a lot of heads together. So this is what we are trying to do now. So we will draw basically multiple heads. Okay, so the idea here is that, so let us say we have some inputs. So yeah, let us say we have inputs. So I have, I think 12. Okay, so it's like 1 2 3 4 5 7 8 9 10 11 12. 1 2 3 4 5 7 8 9 10. So this is our X. As you can see, I have increased the number of X. So now I made it 12 in place of 4 instead of 4, and then the time the sequences are still 1 2 and 3. Okay, so this is basically 12 by so this is 3 and this is 12 the width, and so this is basically of the form X is T by D, where T is 3 and D is 12. Okay, and then we'll look at let us say the multiple heads that we have. So then I can draw the heads, let us say. So this is W0 Q, WK0 and WV0, and then all this so all this takes input from here. Okay, and then we have so and then we have multiplication of these guys. Okay, not here. So after multiplying WQ with each of the X, what we get is, so these are the multiplications, and after doing this, then what I get is these. So I have 1 2 3 4 2 3 4 1 2 3 4 2 3 4. Okay, so these are the query key and so query 0, key 0 and value 0 matrices that I get, and then from using this I compute scaled self attention. Okay, like we did it for the single head case in the previous just before this, right? So this is the so this is the first head basically, and all this goes into this scale self attention layer, and this we call it one head. Okay, so this is our head 0. Okay, so similarly we can have head 2 and so on. So this after doing these operations, the scale self attention, the formula that we wrote, that takes Q0, K0, QV0, and then it produces an output. So one of the reasons is like, why do we need multiple self attention or multiple head, right? So why multiple heads? So basically one of the motivations is, let us say this, Sarah went to a restaurant to meet her friend that night. So if we look into this, then there are many contexts that is going on. So first context is what? So basically the self attention focuses only on one of the aspects. If I use only one of the self attention or one of the head only, then it may focus on only one of the contexts. Let us say what. Okay, so for instance, self attention focuses only on one aspect of the sentence, but there are many other aspects, like where okay, or who, in this case, whom C is going to meet, where C is going to meet, when C is going to meet, okay. So if you use just one of the self-attention, then it may put a focus on one of the words there, let us say what only, okay, and don't won't look into other contexts like who or when. So this helps when you have this multiple heads. So so each of these head, as we know, produces some output, right? And the output that it will produce in this case will be, so let us say the output that it produces, I write it here. So this is 4, okay. So this is the output from the first head, okay. But as you can see, the input is like 12 by 3, but the output is 4 by 3 basically, and that happened because of these guys. They themselves compressed it a little bit, okay. And this is the reason why, I mean, this is the reason why even if I use multiple heads, I will not require too much of the memory requirement. Remember that in the previous description of the tension, I kept the same T by D form for these W, K, and V. So hence they produce the query vectors which were of the same D length, okay, and key vector also D length, V vector also D length. But here with the choice of Q, WQ, WK, and V, we reduce the D to D by H, okay. So WQ 0 is a matrix of the form D times D by H, okay. So then when a matrix, when some vector goes in, it multiplies with W, and then it trims the, or like D by H, I believe. Let me check. D by H, right? That's right. So we have D by H. So then X will multiply with the D, and it will get trimmed, right? So X times WQ, if you do, then the output will be X is T by D. So if you multiply with WQ, which is D by H, so the whole the output that you will get will be T by D by H. So T is 3, you still have that, and D by H, since there are 3 heads, H is the number of heads, okay. So let us say H is number of heads. So in this case, we say that there are 3 heads, let us say, okay. So if we have 3 heads, then one of the other heads will be somewhere here. So let us say I remove this for the moment, and then the other head 2 will be here, and the other head, third head, will be here. So this is my head 3, and this is my head 2, okay. So head 0, I mean, okay, so we are using with indices 0, so this is head 1, and this is head 2. So there are total 3 heads, head 0, head 1, head 2, and they have the same thing going on, but the only thing is that we are giving it more expressive expressions for each of these, because these weights will change. We don't have the weights shared between the head. So this weight, that's why we have the sub index 0. So this corresponds to weights of these head 0, and here we are giving it a weight 1Q, weight 1K, weight 1V. So this is the reason why, like, we want to capture multiple contexts, who, where, when, and that's why we plan to have these multiple heads. So so what you see here is that the initial data, the stack data, you have T by D, but then what you get eventually is T by D by H. So there is a compression also, and this compression is good, because since I have now 3 heads, now if you look into the combined memory, then query, it is T by D by H, T by D by H, T by D by H, and there are how many heads? There are H. So overall, then the memory complexity still remains for the query matrix, which is T by D only, okay. And similarly for the key matrix, it remains that way, okay. So more heads you have, you may prefer to decrease it, although this is something you may change, but the thing is, like, the outputs that I will get here, I want to make the outputs in a way that if I concatenate, so that's my plan, the output that I get here, so output that I get here will be T by D by H, okay. So I have drawn one of the outputs here, so the outputs will be 1, 3, 4, 1, 2, 4, 1, 2, 3, 4. So this is my T, which is 3, and this is my columns, which is 4. So the plan is that I have 3 in this case, so 4 plus 4 plus 4, I want to make it 12, okay. I want to make it same input, same the output to be same dimension as input. And why would I do that? Well, I would do that because because there is a concept of stacking one block on the top. Okay, so that's why transformer sometimes it's difficult to understand, because there is multiple things happening and their stacking is going on. For instance, initially we saw let us say a concept of a head. Okay, but then these heads are multiplied, I mean they are stacked. In this case there are, let us say, 3 heads, but then next we are saying that if the output remains same dimension as the input, then I can repeat this process again with another layer of multi-head attention. So I can have this one block of multi-head attention, and then I can put another block of multi-head attention. I can put that because it conforms with the dimensions, so similar dimensions also flows through, similar metric sizes also flows through in the same way recursively in the next multi-head attention and so on. So so this is the idea behind this. So basically here also it's more or less the same story here. So I have WQ1, and then I have WK1, and then I have WV1, and then these guys get multiplied. I mean they don't get multiplied, they get multiplied with the input basically. So this basically this input goes here, here, and here, and these inputs get multiplied with this guy, and this guy. They themselves don't get multiplied obviously, so we have seen this already. And then in the same story, so it produces T by D by H again. So basically, so here also 1 2 3 4 1 2 3 4 1 2 3 4, and here also. Okay, so then again so that's how we get this Q1 K1 V1, and then it goes into self-attention. So remember, self-attention formula was there. You just have to provide Q1 K1 V1, and it produces the self-attention values after that. So this is scaled self-attention, and then there is an output, and this output will be again T by D by H. So remember, one head produced T by D by H, and one head produced T by D by H, and another head produced T by D by H here also. Okay, so there are these 3 outputs we have, and then we will combine these 3 outputs, and if we combine these 3 outputs, then we will have T by D as an output. Okay, so that's the idea behind multiple self-attention and so on. Okay, so this concatenate output may go through one more way, let us say a linear layer, let us say. Okay, combining these 4. Okay, so to produce the final output. So this concatenate, so let us say this is our head, and then I will use this to show that these 3 outputs can be concatenated like that. And then these are concatenated, and then they may be further go through some D by D linear layer to produce final processing. Okay, so this is these are kind of the next set of steps. So yeah, so this okay, so we will continue this in the next class, so we will stop here.